let's at least just start reminding what was the final thing. So towards the end, we started looking at differential equation one complex variable, right? So differential second order, right. Differential equation in a complex variable. Z. So the equation, I can always write it in the following way. U plus, I think, let's see, P notation, Pz d by dz u plus Qz u equal to 0. So this is the kind of differential equation. As I said before, we were calling it A, B, and C, but you can always divide by A, and this is really B divided by A according to our old notation, and Q is C divided by A. If A has some zeros, that will translate into singularities for P and Q, right? So now we will discuss also. I mean, so far we didn't include the case where A had a 0, right, in all these previous discussions, but now we are going to discuss that. And we had a classification. The solution of the differential equation depends very much on the properties of P and Q. That is obvious because that defines basically what the differential equation is, right? And in particular, if you're looking at some region where P and Q are analytic, okay, no poles, analytic, in that case we will see that the solution, the fundamental set of solutions for the U will also be analytic in that region. Okay, this will be proved today. And when there are singularities, then the solution for the U will also in general have singularities, like branch cuts, things like that. So we need to classify what kinds of behavior. I mean, for different behaviors, answers are different. So we should classify the behavior of P and Q. So one thing is, the first statement is that, let's say, and in all these cases, what we will do is we'll make a power series expansion. We will solve this differential equation so that U will be expressed as a power series around some point Z0. Okay, so we are looking for a power series solution for U around some point Z0. Okay, so looking for power series solution around some point Z0. Okay. So, and then this power series will depend on the behavior of P and Q in a neighborhood of Z0. That's the idea. So two cases, that P and Q, I mean three cases actually, P and Q are analytic in some region containing Z0. So meaning around Z0, there is some neighborhood where P and Q are analytic. Z0. Second, that P and or Q. So second is P or and Q has an isolated pole type singularity at Z0. So these are the two cases. And further we said in this case also, so you notice that it's isolated. What it means is that there is a neighborhood of around Z0 such that the only singularity is at Z0. No other point in that neighborhood there is a singularity, only at Z0. Okay, and then there were two cases here. One was that P has at most first order pole, and Q has at most second order pole. And the other and the remaining cases. So when the poles are worse than this, when the P pole is worse than first order or Q pole is worse than the second order, then that is other class. So the remaining case, remaining singularity cases. Okay. So in this case, you say the Z0 is a regular singular point. Okay. When this happens, then you say Z0 is a regular singular point. And in this case, you say Z0 is a irregular, I suppose. It must be the opposite of Z0 is an irregular singular point. Okay. So that's mainly the distinction between this is that will again show that in this case, in this case, when Z0 is a regular singular point, the power series in general, see what is a power series? Power series will be in general, say U will be expressed as some Z minus Z0 to some power R, and then you have a sum, right? N going from 0 to infinity, Cn Z minus Z0 to the N, right? This is the kind of power series will be. So in this case, it turns out that you can write down both the solutions. There are fundamental set of two solutions, two linearly independent solutions. Both of these solutions can be expressed in this form. Okay. Whereas in the irregular case, it turns out that at least one of them cannot be expressed in this way, and in fact, it can only be expressed by, taking the sum all the way from minus infinity to plus infinity, right? So in other words, the solution will have essential singularity. Because remember, essential singularity, you had the Laurent expansion which starts all the way from minus infinity to plus infinity, right? So that is the case. So we will be discussing only the first case here, and in the second case, we'll only consider this for the time being. In fact, for the next 3-4 lectures, or even more, maybe 5 lectures, we'll be only dealing with these two cases. And then if I get some extra time, what I will do is I will start from these solutions and take some particular limits, okay? In which case the differential equation becomes something which has some singularity at some irregular singularity. So we'll be able to obtain those solutions for that subclass of problems where this irregular singular point appears by taking some limits of the differential equations which contain only regular singular points. In those cases, we'll be able to say something about it. That will appear in the confluent hypergeometric functions. Okay. But as I said, all these previous years, I never got time to discuss confluent hypergeometry. Hopefully, I will get some time this time. Yeah. Was there any question? No. Okay. So let's start with the first one because that's the easiest one, easiest situation where it's analytic. P and Q are analytic around Z0. Actually, yeah. So in this case, I will be. What I will do is not just the power series. This can be rewritten in the power series, but proof will be in a slightly different way, not in terms of power series. So the idea is to first convert this equation in some suitable way. So you see, you can write. Let's say, so if I change the variable u is equal to some function f of z. So u is a function of z, of course. Is some function of z times e to the power of minus half integral from the point z0. We are looking at the neighborhood around z0. First case, we are looking at this case now. So P and Q are analytic. So I can do this integral z0 to z. P psi P say z prime dz prime. Yeah. So and you see that because it's analytic, it doesn't matter what path you choose, right? The integral will have the same value because of the Cauchy theorem, right? Z0 is say here, and we're looking at some region where P and Q are analytic. So so all this z is inside that region. So if z is some point here inside the region, it doesn't matter what path you choose to define this integral. Answer is independent of the path. So this makes sense. Okay. So what is the use of that? Because if you plug that in here, you'll get a differential equation for that, for f. Right? So let's just plug that in here. So du by dz is, they have two terms. There is df by dz times exponential of all that. Okay, I will just put a bracket here instead of writing. Plus the term when the derivative hits here. When the derivative hits here, you get, okay, f times exponential itself minus all that. But then the derivative acting on here, but the z only appears in the limit point, right? So when you take the derivative, you'll just get integrand evaluated at z. So you'll get here minus half times p at z. Those are the two terms. We need also second derivatives. So d2u by dz2 will again give you d2f by dz2 times exponential plus a term when the derivative hits here. So that will give you df by dz, that is that, times exponential. And then the derivative acting there, which was already computed, minus half pz. Okay? That's the derivative acting on the exponent here. Then there will be another term where the derivative, so that's the first term. The second term, the derivative can hit here. That gives you the same term again. So it gives you a factor of 2. Okay. And finally, the derivative hitting this exponential and that. So there will be a term where when it acts here, you will get again f times e to the minus that and square of this, because this was the derivative of that, that exponent, which means 1 over 4th pz square. Okay. And then there will be a term when the derivative hits here, so that the prefactor is the same. So that gives you minus half dp by dz. Okay. That's all. So now we plug that back in here. I mean, it's just convenient to make this change. The reason is that what will happen is that the first derivative term will disappear. df by dz will disappear. That's the reason for doing this. Okay. So if you plug this here, so the exponential is everywhere, right? In all the terms, there will be this exponential, right? The exponential is everywhere. Here, here, and of course in the u itself. So the exponential, I can take it out. So there will be exponential outside. And then you have d2f by dz2 plus from here you get 2 times minus half, so it's minus pz df by dz, and then you have plus f plus 1/4 p square, I mean pz square minus 1/2 dp by dz times f of z. That's from the second derivative. Then the first derivative, you get one term from here, p times that, and that is, you see that cancels. So plus p times df by dz, and then there's a term which is p times f plus p times f. Minus 1/2 p square, right? Because there's a p here, there's a p I'm multiplying, so minus half p square times f. That's that. And then finally plus q times f. Okay. So you see that this cancels. That was the purpose of this. I mean, doing this to get rid of that. Okay. So equation becomes pretty simple. I mean, so this whole thing is supposed to be equal to 0. Well, exponential is never 0, so I can remove that. So basically, the equation on f becomes d2f by dz2 plus something times f. So actually, let me just call it kz. All of this, I mean, take f as a common factor, then it's multiplying all of this. So all that remaining things I just call kz, where kz is all that, which is, so 1/4 p square minus, so this minus 1/4 p square minus half dp by dz plus q. Okay. So it will be again some function. Since p and q are analytic, in this region. Also, the derivative of P is analytic. So, therefore, K is analytic in this region. So, you have a simple looking differential equation. I mean, simpler than that. Okay. Fine. Okay, good. So, now what we will do is, so f satisfies this differential equation, right. So, if we can find the solution for f from here, right, then I can go back and plug it in here and we have found a solution for u, because this is all known functions. P is known function, so this is known and all you need to know is f. So, we will now concentrate on this equation. So, what we will do is we will try to find a series solution. It will not be power series, I mean, at the moment, but you can rewrite it in the power series if you wish. But okay. So, what we will do is we will consider a sequence of functions, f0, f1, f2, etc., which satisfies the recursion relation, which satisfies the following differential equation, type recursive relation. d2fn over dz2 is equal to kz, this kz, let me say no, plus kz fn minus 1z. So, these are all functions of z, of course. That's equal to 0. So, you see it is not exactly that, because here you see the same f appears in both terms. Now, what we are seeing, we are taking a sequence of functions which satisfies the following equation. So, in other words, if f0 is given to you, then you plug that in here, that gives you a differential equation for f1. Similarly, once you know f1, you put it here, then you can find the solve for f2. So, you recursively solve this equation. So, in fact, you can immediately solve this equation. So, for example, if I do one integral, so dfn by dz, I can write it as integral of minus say from z0 to z of k z prime fn minus 1 z prime. Yeah, that will solve this equation, because if I take a derivative, further derivative, only z appears in the endpoint. So, you will just get this evaluated at the z, which is this with a minus sign, because I take it on the other side. So, dz prime. Okay. And now, if I do one more integration, so I will get here fn of z will be equal to, I drew one more integration. So, z0 to z, okay, of integral of this quantity, okay, which is so dz, so let me call it dz double prime. Okay. So, I am evaluating this at z double prime, right, and then integrating this. But as z double prime means it's this z is replaced by z double prime, right, z0, z double prime, k z prime, fn minus 1 z prime, dz prime. There are two minuses. No, it's just one minus. Correct. No, this minus is there. Yeah, that's okay. Yeah. This is a recursive equation. Yeah.
How can we obtain that equation from?
No, not from there. No, this is an auxiliary equation. Our aim is to solve that, right? But we are not solving that for the time being. We are just looking at this equation and solving for this sequence of functions. And then we will show that actually this function f can be written as a sum of this sequence. Yeah. So, if you add f0 plus f1 plus f2 and so on and so forth, that will actually solve that equation. That's what we will see. So, this is this is an auxiliary equation now. I mean, it's not directly that equation, but we will use this to solve for that equation. Yeah. Okay. So, what will happen is that what we will show is that this f will be equal to sum over fn. n going from 0 to infinity. Okay, that's what we show. And of course, we'll show that it's convergent. We'll show that the series converges. Okay, that's the yeah.
I would like F0 verify this equation the first.
Sorry.
F0.
Yes.
If n equals 0, verify this equation.
Yeah. No. For F0 is arbitrary at this stage. F0 is arbitrary.
No, if n equals 0,
Yes.
you can verify this equation.
No. So there is no f minus 1. So that doesn't. I mean, you cannot apply for that because there's no. So I mean, if you wish, this equation is true for n greater than or equal to 1. Yeah. F0 is arbitrary. See, F0 is not determined by anything else. F0 is arbitrary, and actually we'll choose F0 to be just a linear function. So actually, what we will do is we'll just choose F0 of z, very simple function, a linear function. Let's say C0 plus C1 z minus z0, just that.
Why don't we start by saying we can write f as a sum of fn and then we plug this sum there. Then, but I don't know, but we didn't. I mean, if we start from this, then we didn't have this recursion relation.
No, but I mean, you need some kind of a series. See, the point is that all these fn's, as you increase n, they'll be smaller and smaller in the region near z not equal to z equal to z0. Okay, so it'll be like, I mean, normally we would do power series expansion, right? We will say z minus z0 to the n times some coefficient cn. But here I'm not doing that, although this is closely related to it. It's a I mean, yeah. So for example, let's see if you just plug this in, because you see each of this integral, so let's say, I mean this side, there are two integrals here, z, right? If I take z approaches z0, the range of this integral becomes 0, right? So everything goes to 0, right? So this, in fact, not only this goes to 0, also this goes to 0, right? Because after all, z double prime is between z0 to z, and if z becomes equal to z0, z double prime is simply z0 itself. So this integral vanishes. So there's a double 0 here, right? So every time you go higher up in n, you get more and more powers of z minus z0. So if fn minus 1 already was z minus z0 to some power, you see fn will become that power plus something more. You see. So this is really a kind of power series, but not exactly. So the successive terms are smaller and smaller as z goes to z0. Okay. So then okay, we can just try to rewrite this last part in a slightly different way. So what we can do is I can put here dz double prime, I'm sorry, 1, okay, 1 is 1, and then you can write 1 as dz double prime over dz double prime, right, and then do a partial integration by parts. So the structure is, so let's call this whole thing as, I don't know, something, I don't know, some capital A, which depends of course on z double prime, this whole thing. Then the structure of this integral is minus dz double prime z0 to z, and then times A of z double prime, right, where this A is all of that stuff. But then I can do integration by parts, so that this will be this will be equal to z double prime times, so minus, sorry, there's a minus here. Actually, I could have put minus also inside, but anyway, A z double prime evaluated at the endpoints, right? That's the total derivative piece. And then there will be a piece where the derivative hits there. Okay, so you'll get here, so minus minus plus, so this gives you dz double prime z0 to z times z double prime, and in fact, yeah, z double prime, let's say, and then you get the derivative of this, okay. So dA divided by dz double prime. But that derivative, you see, az double prime itself is an integral up to z double prime. So that derivative hits only the end point. So it will just give you this whole thing evaluated at z double prime. So the last piece is, so this piece is actually simply z naught to z dz double prime times z double prime, and then the derivative of that, which is simply gives you k z double prime times fn minus 1 z double prime. Yes, that is when the derivative hits there. And this piece is, so this piece is evaluated at z and z naught, right? These are the endpoints. So when you evaluate at z naught, this a is 0, because when z double prime equal to z naught, this integral vanishes. So a becomes 0, right? So only the upper term survives, the upper boundary. For that it is simply z. So this is minus z times az. But what is az? Az is this integral all the way up to z. So you get here z naught to z k z prime, okay, z prime f n minus 1 z prime dz prime. So this is the thing, right? But now you see the z prime here is, and z double prime is a dummy. I can change, I can call it whatever I want, right? So I might as well, because I want to combine these two integrals, so I just want to use the same dummy variable, okay? So I can just call this as z prime. Okay. Now I can put them together, and you see you get here minus, or I can put it plus, it doesn't matter, z naught to z. See, these two terms I can combine to simply dz prime times z prime minus z k z prime fn minus 1 z prime. Okay. So this is okay. This is just a convenient way of writing it. I mean, the point is that now you see there's only one integral instead of here you have two integrals. So we've just by this trick we have rewritten in terms of one integral. That's all. Okay. So now see the point is that so maybe I should first check this. I should, you see, remember we want to say that let's look at this. Let's consider f equal to that and plug it in that equation, the original equation. Can I erase this part now? I think this part has been used. I keep that equation, but this I don't need now because that's all that. So this is fn z. So what we are saying is this is fn of z. That's the upshot of that analysis. I mean, this is a solution of that equation. Okay, can I erase this part? Okay, so let's take this combination and plug it in here. Okay, so you will get here d2 over dz2 of sum over fn. So fn z sum over n. Okay, that's that. Or perhaps maybe first I should show that this series converges uniformly, because otherwise you are not allowed to commute the two things, right? So maybe first I should show that, right? Because okay, or maybe let's assume that we have shown. I'm going to show it, but let's assume that we have shown that this series converges uniformly. Suppose we have shown it. In that case, this is legal, right? I mean, originally it was that this f is sum over fn, right? But now I can move the derivative inside, because when uniform convergence is allowed to commute the two operations. So I do this infinity, and that similarly here. Okay, here of course I don't have to do anything. So I substitute again f. You remember our original equation was these were f, both were f, right? So I just take this f and plug it in that original equation. So you get a plus k, again sum over n, f and z. Right? So what is this quantity? Let's see. So this, you see, if I'm going to assume that f0z is linear function of z. So on f0, these two derivatives are annihilated, right? d2z by dz2 on f0 will be equal to 0, right? But from not from from f1 onwards, it will not be 0, right? So really this sum goes from, the first sum goes from, I mean the second goes from 0 to infinity, but the first sum really goes from 1 to infinity because the 0th term was vanishing. That was because of this choice. We have chosen that f0 is a linear function of z. Okay. For this reason, it starts from n equal to 1. But for n equal to 1 onwards, we have this recursion relation, right? So this quantity is nothing else but minus n equal to 1 to infinity of kz times fn minus 1z. That is what this quantity becomes, right? But now you can again, you see, you can call this, after all, when n is equal to 1, this is 0, n minus 1 is 0, and when n equal to 2, this is 1, and so on and so forth. So I can as well write this as n equal to 0 to infinity fn, right? And now you see this cancels exactly that, right? So you get a 0 answer. So this is 0. So this is the, so if we can show that that uniformly converges, this series uniformly converges, then we are done. Then we have found a solution for f. Yeah.
Where did this second factor come from?
No, I'm looking at this equation d2f by dz2 plus k f. This is equal to 0, right? This was our original equation, right? Now what I'm claiming is that if I take this f as this series, then that will solve this equation. And what I've done is just to prove that. Assuming uniform convergence of that series. So we need to show the, any question here? I mean, is that clear? I mean, initially it was 1 here, and this is n minus 1, but that's what it is. It's for n equal to 1, it is 0, n equal to 2, it's 1, and so on. So this is simply kz times f0 plus f1 plus f2 plus fn, and the other one is also the same, so it cancels. Okay, so now the last thing is the uniform convergence. Okay. Now what we will show, in fact, is that the modulus of f and z, is bounded by the maximum of the modulus of f0 times maximum of k. Maximum of k. K is this k, right? K which appears here. Remember, k is analytic in this region. Okay, so the maximum is bounded. It's some finite quantity. It's always less than, it never blows up to infinity, so it's going to be some finite quantity. So max k to the power of n times z minus z0 modulus to the power of 2n divided by factorial n. Okay, so we'll prove this now. Okay, but I mean, if you have proven this, then you are done. You see, because if you plug, then I mean, I'm going to prove this, but assume this for the moment. Then you see the modulus of f is less than or equal to sum of n equal to 0 to infinity modulus of fn, right? And modulus of fn we are saying is that less than or equal to that. So this is less than or equal to max f0, because that's a common factor in everything, times sum n equal to 0 to infinity max k to the n z minus z0 to the 2n divided by factorial n. But this is just a series of exponential, right? So this is the same, this quantity is the same as exponential of max k times z minus z0 modulus square. See? So that is a convergent, this is convergent. See? So therefore, the original series is convergent. Right? So that's the idea. So we don't need to prove this now. There are a few steps in proving this. It's not, yeah. So we'll start from this expression. Okay. And prove that. Where is it? Yeah. So let's see. Now, of course, these integrals are. I can erase all this, right? I can erase all this. I mean, we said all these integrals are independent of the choice of the path. We have to do an integral here, right? Because they were dealing with analytic functions. So we might as well choose a straight line path, because we would like to make an explicit estimate of this integral. Okay? So I just choose a straight line path. Then z prime is what? Z prime is equal to z naught plus z minus z naught times t, right? Where t goes from 0 to 1. Right? When t is equal to 0, z prime is equal to z naught. And when t is equal to 1, z naught cancels, and z prime equal to z. So this is the, as you change t from 0 to 1, you go along the straight line. Okay? This is a straight line. Straight line equation for straight line is always linear in some parameter, right? The parameter here is t. So this is a parameterization. Just like you remember for the circle, when you have circle, we always say z is e to the, some r times e to the I theta, and you're integrating over theta, right? Same way here, for the real line, I'm parameterizing the real line by some parameter t. And indeed, you can see for t equal to 0, this is z naught, and t equal to 1, it is z, and in between, it is linearly going, right? It's a line, it's a linear. So therefore, basically the dz prime I can write. So the integral becomes 0 to 1, right? Z naught in the t variable. And the dz prime simply becomes z minus z naught times dt, because it's a t which I'm changing, right? So dz prime is simply, I mean, z naught is a constant, so you just get z minus z naught times dt. Okay. Furthermore, if you look at z prime minus z, substitute the z prime there. So you see what you get. So I have to subtract from here z. So you get z naught minus z plus z minus z naught times t. But again, I can take out, say, z naught minus z, then you get here 1 minus t. Yes? I mean, this is z prime minus z. Because when you subtract z, you get a z naught minus z, but then that becomes a common factor in these two terms. But there is a minus sign because this is z minus z naught. So you get 1 minus t times z naught minus z. Okay. Times the remaining things, which is k of z prime, which is okay, k of this z prime, where z prime is given by this, and similarly fn minus 1 z prime, where z prime is now is a function of t, right? So everything is a function of t now. So this is fnz. So let's see, let's look at the absolute value of fnz. And by the way, these things are t independent, so I can take it out of the integral, right? So you get essentially, so when I need some space now. So I can erase this part now. Also remove this piece here. Okay. So we get this conclusion that fn z modulus is less than or equal to the z. There are two factors of z minus z naught. So it becomes a z minus z naught modulus square. Is modulus, so I don't care about the minus signs and so on, absolute value. And then 0 to 1 dt, and the absolute value of the integrand, which is, okay, there's a 1 minus t, and then the absolute value of integrand k z prime and f n minus 1 z prime. Okay. So the proof of this statement will be by induction, actually. We will assume that up to, say, n minus 1, this is satisfied, this bound is satisfied. Then we will show that fn will also satisfy this bound. That's the idea. Okay. This is by induction.
So what we did is just we write f as a series of z minus z0.
This is not really a series, right? No, this is not. Yeah.
I think n represent like fn is z minus z0 raised to n plus 1.
Yeah, well, I mean, so this is not exactly that, because I mean, This is a bound. Fn z is not simply z minus z0 to the n times some number. It's a non-trivial function of z. I mean, it's not just that z minus z0 to the n, but there will be other terms also. Yeah. For example, let's say just imagine, suppose k was 1, kz was simply 1. Let's suppose simply. So I take say just even compute f1. So f1z will be in that case simply z0 to z, z prime minus z dz prime times k is 1, and let's say the fn minus f0 is a linear function. So you get here c0 plus z prime minus z0 plus times c1, right? Now when you integrate it, it won't be simply z. I mean, the result will not be simply z minus z0 square or z minus z0 to the 1. There will be various terms. Okay, it's not. I mean, I think that's clear, right? I mean, this I can write it as z prime minus z0 plus z0 minus z, right? And you integrate this quantity, you see there will be various powers of z minus z0 will appear. It's not just single power of z minus z0. Yeah.
Okay. It looks that kind of.
I mean, there is a bound. You see that this is less than or equal to that, right? So indeed, as you increase n, this one, as you increase n here, this z minus z0 to higher and higher powers appear. Right? That's why I'm saying that this is a little different from power series expansion. Although in the later part, when we discuss a regular singular point, we'll be always doing the power series. This is a slightly different approach, but finally it can again be, you can recombine everything into write in terms of power series. Okay, so this is so let's see what we get here. Yeah, I think there are some little steps here. Z prime, yeah. So now we are proving by induction, by induction. Okay. So assume that this bound is true. In other words, assume that the bound is true. True for fn minus 1. Suppose this equation is true for fn minus 1, then we'll show that this is also true for fn. Assume that then. Okay. Then we'll show. Then we will show that this bound is true also for fn. Okay, so we again start doing this. So this, of course, I can replace by max. I mean, after all, we are looking at a bound. I can replace by the max k and take it out because max k is independent of the t. And fn minus 1 z prime will be given by that. So let's see. So this continuing from here. So what it says that fn z absolute value is less than or equal to z minus z0 square, and then max kz. Max k times integral dt. So let me write it like this: integral dt 1 minus t. Now max n minus 1. So you just substitute wherever you see n, you substitute by n minus 1, right? Because we are assuming that this bound is true for fn minus 1. So you get a max k to the n minus 1, which again I can take out of the integral. So altogether it becomes, the power becomes, there's a 1 from here and n minus 1 from that. So you get power n here, okay, and then you have a z minus z0. Okay, here is z prime. So I should look at z prime minus z0 to the power of 2n minus 2, because n should be replaced by n minus 1, and then there is a 1 over factorial n minus 1. Okay. But now, what is z prime minus z0? Remember, our parameterization was z prime is equal to z naught plus z minus z naught times t, right? That was the parameterization. So z prime minus z naught, you take the z naught on the other side, is simply z minus z naught t, right? So this quantity is z minus z naught to the power of 2n minus 2 times t to the 2n minus 2. So indeed, the z, you can take also this part out because this does not depend on t. So you see this becomes 2n. See, we are coming closer and closer to that now. Okay. So I take this. So therefore, this is the same as fn z absolute value is less than or equal to z minus z0. Okay, let me write first max k to the power of n, and then z minus z0 to the power of 2 plus 2n minus 2, which is 2n. And then I have 1 over factorial n minus 1. And then I have to do this integral, which is simply a very simple integral, dt 1 minus t, t to the 2n minus 2. Okay. But this integral from 0 to 1, this is integral you can explicitly do. But anyway, we don't need to do explicit because we are looking for a bound. Okay. So I can replace 1 minus t by 1, right? We are looking at upper bound. After all, 1 minus t is always less than, in this range, is always less than maximum, I mean, always between 0 and 1. So I can replace it by 1. Okay. So I mean, because that is because we are looking at upper bound. If you are looking at lower bound, it would not be. You cannot do that. I mean, of course, this integral you can explicitly work out, but I mean, just to save time. So this you can replace it by 1, and that integral is simply 1 over 2n minus 1 times t to the 2n minus 1 integrated between that. So that gives you 1. So all this integral is bounded by 1 over 2n minus 1, right? Actually, 1 over 2n minus 1 is even less than 1 over n, right? Okay. So I might as well replace it by n because I'm looking at an upper bound. For n large, I mean 1 over 2n minus 1 is going to be always less than 1 over n, right? For any n larger than 1. So even this is okay for upper bound. So that gives you 1 over factorial n, which is what that thing was. You see, we had already everything else. Oh, sorry, there's also max f0. I forgot about that. Because in the fn minus 1, there's also, but that's again, I can take it out, max f0. So there is also max f0. That's there. Okay. So what we have proven is that this is true. I mean, this bound is, if this bound is true for n minus 1, then this is also true for fn. So by induction, it is true if you can prove the first one. If you can prove that for f1, this is true, right? If it's true for f1, then it's also true for f2 and so on and so forth. But f1 you can explicitly integrate. F1 is simply here, it will be this times f0. And I mean, I'm not going to do it, but you can just do the same thing, change the variable from z prime to t, and you can show that for f1, this is indeed true. For n equal to 1, what happens? You have a max f0 times max k, n equal to 1, max k, and z minus z0 square divided by 1. But that was already there because you see, max for n equal to 1, max k comes out, here is f0, so max f0 comes out, right? And then this gives you, the change of measure gives you, remember, z minus z0 square. One from the, when you change the dz prime will give you z minus z0 times t. And the other guy, z prime minus z, also gives you a z minus z0 factor, right? So that integral, so actually let me just do it. So f1, you can do it exactly the same way. This gives you, this gives you, so that measure, I mean, I just erased that unfortunately. No, it's here. This is here, right? I mean, yeah. So I mean, yeah, you can explicitly see for f1 this is indeed true because this is less than or equal to z minus z0 mod square times integral 0 to, I mean, you can take out max k, and in this case f0, so max f0, and then the integral that's left over is simply this integral 0 to 1 dt 1 minus t, right? And this is certainly, if I replace this by 1, it is certainly less than that, right? But that integral is simply 1. Okay? Actually, this integral is half, but half is less than 1. That's where this is for. So this is certainly true for f1 explicitly. And now what we have proven is that if it's true for n minus 1, it's true for n.
Here, we had some integral 1 minus t raised to 2n minus 2 dt. If we put n is equal to 0, we have 1 minus over t squared. And
Hey, sorry again.
1 minus t,
Yeah. So this is the 0 case.
t raised to 2n minus 2. T raised to 2n minus 2.
T raised to the power of 2n minus 2.
Minus 2.
No, that is not. No, that. That's probably true for n. Here you explicitly see this is the integral, right? So how the t to the n minus 2 came? That was by using this bound, right?
Yeah,
But
okay.
yeah,
Then if we put n is equal to 0,
yeah. No, you cannot use that. You have to use directly this relation. Directly use this relation.
alright. But it doesn't work for n is equal to 0 because we will have ln of something and then which diverges for.
Um,
N equal to 0 is not this case because we assumed before that
Yes. Yeah. Right. So for n equal to n equal to 1, which is this will be 0. You directly estimate it. You directly show that that satisfies the bound. And then for the remaining guys, you use induction. Yeah. So that proves that. So finally, what happened? So with this bound, we showed that this series, modulus of the series, is bounded by the exponential, right? That series was exponential, but the exponential series is uniformly convergent for any finite value of z, right? So in principle, you would say that it's defined in the entire complex plane, but that's not the case because we have a max k here. You see, that means that this is valid only in the region where k is analytic. You see, so. So suppose you have a near z0, some neighborhood p and q are analytic. So therefore, k is also analytic. Okay, but then if beyond that, maybe there is some point where you have a singularity in p and q, right? So you cannot extend beyond that because there max k would become infinite, right? So that you cannot trust that. So you can only trust this even though the exponential series is uniformly convergent for the entire complex plane. But the point is multiplying something which may blow up, right? So this is really only in the region where. So basically, the convergence is from the z0 you go all the way to the nearest singularity in the functions p and q, right? So radius of convergence will be up to that. This series. Okay. 30. So of course, one more thing I didn't say. So now, all of the solution is completely determined once you specify f0, right? Because from f0 you get f1, from f1 you get f2, right? But in f0 it was a linear function, so there are two constants. Okay. So let me then go back to the. Okay. Can I erase all this? Is there any question on this? The proof of uniform convergence. Okay, so maybe I should. Okay, maybe I can erase this part. So f0 was this linear function. We needed to use that fact because remember when we plugged that series in the original differential equation. There was a one term which was d2 f0 by dz2, right? If that was not 0, then the series would not be the solution of the original differential equation. Okay, I remind you, you have d2 when we plug it in, you have a d2 fn by dz2, n equal to 0 to infinity first, and then you have a plus k n equal to 0 to infinity of fn, right? Yeah, here there was this is the same. This term is the same as the n equal to 0 term, which is d2 f0 by dz2. This had no recursion relation. For f0, there was no recursion relation. The recursion relation started from f1 and so on, right? Plus n equal to 1 to infinity of d2 f1 over d2 fn over dz2, but these guys had a recursion relation, right? And these were simply minus k times minus sum n equal to 1 to infinity k f n minus 1z, right? Okay, this cancels with that, but there will be still this term, right? That's why it was crucial that we had to choose f0 as a linear function, okay, so that this vanishes. Okay. So upshot is that, but then once you choose f0 which satisfies, which is a linear function, then everything else is determined by these recursive equations, right? So the only freedom is the choice of f0, and then everything is fixed. But f0 itself was a linear function, which was let's call it c0 plus c1 z minus z0. Okay, so you have two constants, two complex constants, because now we are talking about complex functions, right? So two complex constants are there, but that we anyway knew. The second order differential equation must have two parameters. Solution must have two parameters, and those are the two parameters, right? In fact, they are actually just giving you the boundary condition. You see, I mean, if you take the value of fz at z0, at z equal to z0, well, that's going to be simply, so let's see, so that value is the sum, the value of the sum fn z0, right, n equal to 0 to infinity. But the point is that all the higher ones, n, I mean f1, f2, etc., they will vanish at z equal to z0, because looking at this integral, right, this will vanish. No? So you see that only term which can survive is f0. I mean, what I'm saying is that from this equation it's clear that fn z for n greater than or equal to 1, the fn z0 is equal to 0 for n greater, because this is for n greater than or equal to 1, right? Okay, but if you put z equal to z0 here, this becomes z0, the range of the integral becomes 0. I mean, it's the same point, so result is 0. Okay, so this is in fact simply f0 of z0 at evaluated at z0, because all the higher terms are 0 anyway. But that is c0, right? So c0 gives you the boundary condition of the value of f at z equal to z0, right? What about the derivative? If I take a derivative df by dz at z equal to z0, that's the same as taking the derivative, because again uniform convergence. For that reason I can take it inside at z0. Now again let's look at this equation. So if I take for n greater than or equal to 1, so let me just write here n greater than or equal to 1, dfn by dz is equal to, well, the z appears only there, right? So it's just this expression evaluated at the endpoint, at z prime equal to z, right? But at z prime equal to z, this is 0, right? So this is 0 again, right? So once again, this thing simply becomes df0 over dz at z equal to z0, and that is c1. So these two constants c0 and c1 are the value of the function and the value of the first derivative of the function at z0. And once you specify these two numbers, you determine the solution. So it's a two-parameter family of solution, as we. So you can just so this gives you a fundamental set of solution. For example, you can choose one solution with c0 equal to something constant and c1 equal to 0, and the second solution c0 c0 equal to 0 and c1 not equal to 0. So that gives you two independent solutions. Okay. That's it. It's a power series, of course. I mean, now what I can do? Yeah, let me just still we have time, so we can. Maybe I can show an example. So, should I do an example or go on with the? Because I mean, the really interesting thing is this analysis near regular singular points. Okay, this one, okay, this just guarantees to you that near a point where where this coefficient functions p and q appearing in the differential equation, if they are analytic, then the solutions, both the solutions of the second order differential equation is also analytic in that region. But really interesting things happen at the singular points. So, but maybe before that, I can just give one example of this situation where we have. I mean, yeah, maybe because it will connect to the previous chapter. Okay, because this example will be the Hermite differential equation. Okay, and we'll try to obtain the recursive this series solutions. And actually, we'll just use the power series in that case. In fact, I mean, we could have done all of these things by using power series rather than this fn. So you could have just expanded in terms of Cn z minus z0 to the n. And then you would get some recursion relations for the Cn's and so on. But I think to prove the uniform convergence, it was easier this way. That's the reason why they have given the proof in this way. Okay, so consider the example, Hermite equation, Hermite differential equation. Okay, which was, if you remember, it was d2 u by, okay, what you have seen was in the real variable, where we just replace x by z. So it's the same equation, same differential equation. d2 u by dz2 minus 2z du by dz plus 2 lambda u equal to 0. Actually, for the Hermite equation, this lambda was an integer, n. Okay? And the solution of that was hn. We called it hn. But let's consider arbitrary. And we will see something interesting happens when you choose lambda equal to n. But for the moment, I just keep that as it is. Okay, so and let's look for a solution of the form u equal to some power series Cn z to the n. So we are looking at z equal to 0, around z not equal to 0. We choose z not equal to 0. Okay. Anyway, it's regular. The coefficient function, both this is z, and that is just a constant. So at z equal to 0, it's regular. So we choose z not equal to 0. I mean, p is simply minus 2z, and q is simply 2 lambda. This is a constant, and that is clearly has no pole. Right? So at z equal to 0. Okay. So I choose that, and then I just write Cn z to the n. I look for a power series solution around z not equal to 0. So n equal to 0 to infinity. We write this. So plug that in here. So you'll get so two derivatives. You get here Cn times n minus 1 z to the n minus 2. Right? When I plug it in here, and then from here you'll get. So this is again n equal to 0 to infinity. Actually, you see this since two derivatives are there, really it starts from n equal to 2, right? Because n equal to 0 and n equal to 1 are killed by two derivatives. So it's really from n equal to 2, which you don't need to really worry about, because even if you had put n equal to 0, it didn't matter, because then the coefficient, you see, this will be 0 at n equal to 0 as well as n equal to 1. So I mean, it was not important, but just to, okay. Then look at this guy. So this guy gives you Cn, and now one derivative times n times z to the n minus 1, but I'm multiplying by z. So it gives you back z to the n. So minus 2 z to the n equal to, okay, again for n equal to 0 it vanishes, but so it's really from n equal to 1 to infinity. But again, as I said, you could equally well put 0 here, because anyway this coefficient vanishes for the remaining terms. So. And then finally the last one, which is plus 2 lambda Cn z to the n. This is equal to 0. So now you see that this equation relates, I mean, if I now collect, I mean, this is an equation, right? It means every power of, this is of course infinite series in z to the n, right? But the coefficient of each z to the n must vanish. because this whole thing is equal to 0. Right? So let's see what do we get here. So let's look at the lowest power, for example, z to the 0. So if I look at z to the 0 term, what are the terms we get here? Z to the 0, you get 2 lambda C0, 2 lambda C0 from the last term. This one, if you put n equal to 0, this vanishes. So this doesn't contribute. But here, to get z to the 0, I must put n equal to 2 here. But when I put n equal to 2, you get here plus C2, C2 times 2 times 1, which is 2. That's equal to 0. So this tells you C2, you can, once you choose some C0, then C2 is determined in terms of C0. So maybe I can just write the general expression, because this has to be true for every n. So let's change I mean, here these are n, right? This is n minus 2, but after all, this n is a dummy, right? I can call this n minus 2 as n. Okay, so then this becomes, so I'll call, say, n minus 2 equal to n prime, and then I will later put n prime equal to n. So n is equal to n prime plus 2. So this gives you c n prime plus 2 times n prime plus 2 times n prime plus 1 times z to the n prime. And this sum, you see, n is going from 2 to infinity, which means n prime is going from 0 to infinity, right? So then I can remove the prime here, right? Because after all, this is a dummy. Okay. And now I can combine everything. So this becomes, everything is a coefficient of z to the n now, you see. So this becomes minus 2 times n plus lambda times Cn. So this is a very simple recursion relation. So the recursion relation is, so we want to set this equal to 0, because this coefficient of each z to the n must be 0, right? So this tells me that Cn plus 2 is equal to twice n plus lambda divided by n plus 1 times n plus 2. Cn. This is the equation. So in particular for, so for example, for n equal to, let's see, for n equal minus, oh, maybe, I think I have a minus here. This is, what is it? Minus 2n, n minus lambda, right? N minus lambda. So n minus lambda. Okay. So if I put n equal to 0, you see that you get that, no? Because n equal to 0, this is 1, that is 2, 2 cancels. So C2 is simply minus lambda times C0, which is that. And but this is general expression, no? So given C0, you can determine everything completely. Now you see that, okay, so this is its power series solution, and it's fine. I mean, you know, for any value of lambda, this is well defined. I mean, this will give you a solution, a convergent series. Okay. But in fact, the two things to note. One is that n is related to n plus 2, right? So if I start from C0, then you will determine C2 from these equations, then C2 will determine C4, and so on and so forth, right? So all the even terms you will determine from C0. But if you start from C1, it will determine C3, C5, and so on and so forth. So you have a choice. You can either start from C0, I mean from, say, 1, in this from 1, C0 means I start from 1. And then it will be a even powers only, right? 1, z square, z to the 4, and so on and so forth. Similarly, if you start from the odd power z, then it will give you z cube, z5, and so on. So there are two types of solutions, which one involves only the even powers, other involves only the odd powers. Of course, you can take linear combination of them. In that case, it will have no evenness or oddness. But okay, so this is one structure. Second is that if you had chosen lambda equal to some capital N, positive integer, you see what this tells you, that C capital N plus 2 will become 0, right? So if lambda is capital N, then when small n becomes capital N, this vanishes, right? So which means C capital N plus 2 vanishes. But once C capital N plus 2 vanishes, then C capital N plus 4 also vanishes, and everything, N plus 6, everything vanishes from this recursion relation, right? So the polynomial becomes this infinite series collapses to a finite number of terms, right? That is that's why, I mean, for Hermite polynomials, this lambda had to be a positive integer, right? Say when let's say this lambda is capital N. In that case, what we are seeing is that this expansion stops at C capital N, which means is an nth degree polynomial, right? And that's why we call it H A capital N, which is an nth degree polynomial. And furthermore, you also remember that in Hermite polynomials, depending on n odd or even, it was either only even function of x or odd function of x. So this is the structure here. If on the other hand lambda is not an integer, then this will be an infinite series. But it's fine. I mean, it's still an analytic solution, and parameterized by basically C0 and C1 again, right? Because once you know C0, once you specify C0 and C1, everything else is determined. So which is to be expected, two solutions. Okay. I mean, maybe you can even check it explicitly. Well, I mean, anyway, we knew that Hermite polynomial satisfies this equation for lambda equal to capital N. So this series should give you, this series for lambda equal to capital N should give you the Hermite polynomial. Okay, maybe I can start the discussion. There's no point. I mean, because it's yeah. Okay, so shall I move to the? You want to write something here from that part? So I'll just see. Can you raise this part, right? And this is the okay. This is the example. So now we go to the more interesting case, which is Z0 is a regular singular point. Regular singular point. What it means is that going back to this equation, d2 u by dz2 plus p pz du by dz plus q z u, that's equal to 0. In this equation, since it's a regular singular point, what we are seeing is that p has at most first order pole at z0, and q has at most second order pole at z0. That means if I multiply z minus z0 to p, that will be analytic, right? Because p has at most first order pole. So this will be analytic. And similarly, if I multiply z minus z0 square to q, that will be analytic again. That's because q has at most second order pole, be analytic. So let me call this as A, capital A, and this capital B. Yeah. So since A, capital A, and capital B are analytic, there will be you can make a Taylor expansion around Z0. So I will write A of Z0, A of Z equal to some coefficients which I will call again AN, Z minus Z0 to the n equal to 0 to infinity, and BZ equal to Bn, Z minus Z0 to the n equal to 0 to infinity. That is because A and B are analytic. And furthermore, you know that from the Taylor expansion, there is a I will need this to prove the convergence issues and so on. I will need this, so let me just write it down somewhere in a corner. You know, from the Taylor expansion, I mean, these coefficients are just obtained by as contour integrals of A and B with some suitable powers for Z minus Z0, right? So the precise formula was AN is 1 over 2 pi I contour integral gamma of A Z prime over Z prime minus Z0 to the n plus 1 dz prime and Bn was again the same thing, except A replaced by B. This is n plus 1. Where what is gamma? So the picture is something like this. I have z naught some point here, and this we are saying is a regular singular point. But in the neighborhood, there is some neighborhood where there is no other pole. So we are always considering isolated singularities. Okay. So that means, so there is some neighborhood. So I will choose gamma to be some circle of say some radius r, and that this is gamma, and that is inside this neighborhood. Whatever that neighborhood is, where function is A and capital A and capital B are analytic. Okay. Except at, is analytic everywhere. Okay. Or in other words, little p and little q are analytic everywhere in this region except at z naught. And I choose this gamma to be some circle surrounding the z naught of radius r, which is entirely contained inside this region. So that's the gamma. Okay, so this we will need that to estimate to prove the convergence, this integral expressions. But for the moment, let's proceed. Okay. So this was the these functions are given to you, right? P and Q are given to you. So you know precisely what is capital A and capital B. So in principle, you know precisely what is little a and little b and r by computing these integrals, right? But our job is of course to find out what is u. That is unknown function, right? So let's again look for u, a solution, the power series around z naught. But now I must allow for some possible singularity, right? See, because P and Q are not analytic there, they're poles. So in principle, U may have also some singularity, right? So I will allow for that by putting a extra the power. This R could be negative or fractional, may not be positive integer, right? So I'm allowing for that here. And of course, the equation will determine what this value of R is. But for the moment, I'm just allowing for this possibility that U may have singularity. And then I consider Cn z minus z naught to the n going from 0 to infinity. So you see what I'm doing is I'm looking for some solution of the form where there may be some singular behavior, but then what multiplies it is still analytic at z naught. So the singular behavior is I'm capturing from. That's the reason why I allowed this R. Now I just plug that in here. Okay. It's a bit of a mess actually. And so we just have to plug all these expressions there. So let's see. So I take two derivatives here. So I will get. So this is n plus r. Each term is n plus r. When I take the derivatives, you will get n plus r times n plus r minus 1 times Cn z minus z naught to the power of n plus r minus 2, right? I just put that together here and take two derivatives. So that's the first term. This is n is going from 0 to infinity. Plus now P itself is capital A divided by z minus z naught, right? P. So it gives you a kind of a So this becomes okay. Let me put as it is. So this becomes let me not use the n, but let's say m equal to 0 to infinity am times z minus z0 to the m minus 1 because p is a divided by z minus z naught. So when I substitute, so this capital A was n, so if I divide by z minus z naught, it will be n minus 1. Right? N minus, so m minus 1, I'm using this dummy index m. This multiplying, so that is one term. This is multiplying du by dz, which is some, let's say, k equal to 0 to infinity, and you will get here k plus r times, this is too much. Let me write in the next line. So plus am times z minus z naught to the m minus 1 times k plus r sum k plus r ck z minus z naught to the k plus r minus 1. Yeah. So there is this whole thing. This is each is a product of two series. This is the m from 0 to infinity. This is k from 0 to infinity. Right? It's a product of two series because p itself is a series, and the du by dz is also a series. So and du by dz, I just use the expression. So single derivative, I call this k, and this is k plus r. So k plus r times z minus z naught to the k plus r minus 1. And finally, the last one, q. So you get here now again a product of, so m equal to 0 to infinity, bm z minus z naught to the m minus 2 now, minus 2 because q is b divided by z minus z0 square. So it's minus 2 times again u, which is ck z minus z naught to the n plus so k plus r. So again, it's a product of two series. Okay. So this is the equation. So this whole thing is supposed to be equal to 0. So 0 is equal to all that.
We have some quotient like m times an.
Sorry, m times?
Exactly.
Here, you mean?
Yeah.
I mean, this is simply p. P is capital A divided by z minus z. Du by dz has this k plus r. Yeah. And this one has nothing because there's no derivative, the last one. So let's put them together in a kind of some convenient way, because after all, what we'll do, again, we'll take a particular power of z minus z0. I mean, each coefficient of each power of z minus z0 must be vanishing, right? Because this whole thing is 0. Now, another thing you notice, now, you see this, I mean, what is the lowest power here of z minus z0? Well, that will happen for n equal to 0, right? For n equal to 0, the lowest power is r minus 2. R, we don't know what it is, but whatever it is, it will be r minus 2, right? And look at this term. The minimum power of this is m equal to 0. Minimum value is minimum power will appear when m equal to 0 and k equal to 0, right? Which case again you see you get r minus 2, right? And similarly here the minimum possible value is m equal to 0 and k equal to 0 and again r minus 2, right? So you see every term, in each of these terms, at the lowest power that comes is z minus z0 to the r minus 2. Okay, this is why is this happening? This is happening because precisely we are using regular singular point. You see, I mean from where that minus 1 came, here this minus 1. This minus 1 came because we are saying that this is adverse first order pole, right? Suppose the pole was higher, then this power would be higher here, right? And in that case, okay. Similarly, the reason why this became minus 2 was because we said q has adverse at most second order pole, right? That is the reason. I mean, that's why regular singular point solution behaves differently, whereas in irregular it behaves differently. Because in irregular, these different terms will come with the worst lowest power, right? And then you cannot, it just goes, I mean, there will be one of the solutions will go all the way up to minus infinity. That's the reason for this. Okay, so now we get just an equation for this. I mean, I just combine them together. So this is a matter of just changing. You see, if you put together the power here, and just to show you one in one case. So you get z minus z0 to the power of m plus k plus r minus 2, right? When you multiply this thing, right? And I have a double sum. So this is multiplying am times k plus r, and I have a double sum m equal to 0 to infinity and k equal to 0 to infinity, right. But let's do the following. Let's call this m plus k is equal to n. Okay. Then I can rewrite this sum as z minus z. So call m plus k equal to n, and let's say so therefore this tells me that m equal to n minus k, right. This equation tells me. Okay. So then I can write this double sum as n equal to 0 to infinity and k equal to 0 to n. Why n? Because you see both m and k are non-negative integers, right. Now m is equal to n minus k. So m better be non-negative. That means the range of k can only be from 0 to n. If k is more than n, m will become negative. But that is not the case. M is starting from 0 to infinity, and k is also starting from 0 to infinity. So by changing this variable m and k to n and k, you get that range. And this becomes z minus z0 to the power of n plus r minus 2, and that becomes a n minus k times k plus r. Okay. Similarly, if you do the same trick here, again you see that when you collect the two terms, you get z minus z0 to the power of k plus m plus k plus r minus 2. Right, it's the same form, Okay. Again, call m plus k is equal to n. So the last term gives you again by changing the variable, changing the summation variable, n equal to 0 to infinity and k equal to 0 to n, z minus z0 to the power of n plus r minus 2, and then you see m is n minus k, so that makes it b of n minus k, that's it, times nothing, right. There is no other factor here. Okay. So we have succeeded in writing the second and third term in this form, where I have there is a summation over n. I mean, it's of similar form as that, right. There is a summation over n with the power z minus z0 to the n plus r minus 2. So now I can equate the coefficient of a particular n plus r minus 2, and equate that to 0, right. So you get, so finally the equation you get is, so from here you get, so look at that, so you get n plus r, so I mean the coefficient of z minus z0 to the n plus r minus 2. We are looking at that. So from the first term you get that times n plus r minus 1 times Cn. Okay. From the second term we get, okay, n is fixed because I am looking at a particular power. So we have just a sum. So you get here plus sum k equal to 0 to n of a n minus k times k plus r plus b n minus k. This is from the second and third term. Oh, I forgot something. There is a ck. Yeah, there is both terms have a ck times ck. That's equal to 0. Sorry, there is something. Yeah, that's correct. Now, if you look at this expression, so you see that what is this sum is going from k equal to 0 to n, right? So ck here, I mean c's are unknown. We have to determine c's. I mean, once you determine c, then you know the original. I mean, remember u was this. U was z minus z0 to the r times cn z minus z0 to the n, right? So our goal is to determine cn, right? I mean, starting from some once you know C0, then can you determine the C1 or C2 and so on and so forth. This is a question here. C0 I can choose anything, right? After all, it's a linear equation, so you can multiply if you give me one solution, I can multiply by any number, and you get again another solution. So C0 I can fix it to 1, for example. Okay, but so this is going from 0 to n, and that is Cn. Okay, so you see, I can determine Cn in terms of the lower C's, right? That is what one is saying here. But on the other hand, this this is equal to 0. On the other hand, in this, there is also a term when k is equal to n, so Cn is also there. So it's better to put that Cn term together here, right? So the Cn term will be this. I can rewrite it as n plus r times n plus r minus 1. So we are looking at k equal to n, right? So k equal to n means this is 0, right? So plus a0 times k plus r, n plus r, k is n, exactly, n plus r, and plus b0, right? This whole thing is multiplying Cn, okay, and then the remaining part, which is going up to n minus 1, because I have taken the n part and put together here. So up to n minus 1, a n minus k, k plus r, plus b n minus k, ck. So now we have really a recursion relation. So if I know all the c's up to n minus 1, then this equation tells me what is Cn. So this way you recursively do it. So for example, you start from say n equal to 1. So this equation will give me C1 in terms of C0, right? Because for n equal to 1, only only k is equal to 0. So only C0 appears here. So C1 is determined in terms of C0. Then you go back, put n equal to 2. So C2 is given in terms of a combination of C0 and C1. But C1 has already been determined in terms of C0, right? So you determine C2, and so on. You keep going like that recursively. So this is the idea. So in particular, let's look at the lowest one. You see, I mean, if you look at, I mean, what happens to n equal to 0 term here? You see, for n equal to 0, I mean, it's better to look at that equation. If I look at n equal to 0, this sum, there's only one term, k equal to 0, nothing else, right? So you have a C0 and C0 here also, nothing else. So you have something multiplying C0, and that should be equal to 0. So in other words, for n equal to 0, this term is not there, because how I obtained it, I removed the nth piece from here, and I wrote the remaining integral, remaining sum. But if n equal to 0, there is only one term, right? So really, in this n minus 1, so we should remember that this term exists only for n greater than 0. So n greater than or equal to 1. Okay, this term. For n equal to 0, this term is not there. So it's a bit misleading. By writing like this, you would say 0 to minus 1. What does it mean, right? But it's not there, because I just removed one piece from there, and what is left, there's nothing left there, right? So this is there only for n greater than or equal to 1. But look at the n equal to 0 term of the equation. For n equal to 0, it simply becomes r times r minus 1 plus a0 plus b0 as a0 times r plus b0 equal to times c0 equal to 0. So this equation is for n greater than or equal to 1, and for n equal to 0, the equation is this. Now this is the most important equation. See, because this is C0 cannot be 0, because by definition, you see, when we wrote it like this, what we are saying is that the smallest power, the leading term I take out. I mean, if C0 was 0, then C1, I can start from C1, so I can take one of that power inside and redefine R. So without losing generality, once I take the leading power out, then the coefficient C0, I can always choose it to be 1 or something, right? I mean, non-zero, right? So C0 is non-zero. That means the only way this can be 0 is if this term is 0, what multiplies C0. So that's a quadratic equation for R, because A0 and B0 are given to you, you see. And if you look back at what is A0 and B0, A0 is So I mean that I have to, yeah, maybe I did it right. So let me write it somewhere here to understand what is A0 and B0. I think this I can erase. In fact, A0 and B0 are exactly the coefficients of the first order pole of P and the second order pole of Q, right? Because P was capital A divided by Z minus Z0, so its expansion will be, it will be A0 over Z minus Z0 plus A1 plus A2 Z minus Z0 and so on and so forth, right? And similarly Q, which was B divided by Z minus Z0 square, that is B naught over Z minus Z naught square plus B1 Z minus Z naught and so on, plus B2 and so on. That is the Laurent expansion for P and Q, right? So in this equation, I mean, we have to set this equal to 0. In this equation, what is entering is the A naught and B naught, which are the coefficients for the first order pole of P and the second order pole of Q. So it's really these coefficients determine completely R, right? It's a quadratic solution equation, so there will be two roots, right? But whatever it is, the R, this pre-factor which you have to put it in the U, that power is determined entirely by the values of A naught and B naught. Yeah, that's very important. So I mean, suppose for example it was analytic. In that case, if both P and Q were analytic, A naught would be 0 and B naught would be 0, right? In which case these guys disappear and the equation simply becomes R times R minus 1 equal to 0. There are solutions are R equal to 0 and R equal to 1. Yeah. So I mean, yeah, okay. So it will have no branch cuts or anything like that, right? Okay, it will turn out that, I mean, we still have B1, you see. At the moment you have A naught and B naught only. Okay. I mean, we'll come to that, subtlety. There is some subtlety here. So what I'm trying to say is that the leading behavior of the solution near Z equal to Z naught is governed by these coefficients, A naught and B naught, the singularity. So in general, there will be two roots. I can erase now this part. Yeah. So there will be two roots. Let's call it R1 and R2. Let's rewrite this equation. So R square minus 1 minus A naught R, this combining this linear term and that term, plus B naught equal to 0. This is the most important equation actually. It's called the indicial equation. Is most important because this value tells me the behavior, leading behavior of U near the singularity, right? So it will have in general two roots, R1 and R2, two roots. In general, complex, right? But of course, as you know, R1 plus R2 is 1 minus A naught, right? And R1, R2 equal to B. That's what from the quadratic equation. Okay. Now, okay. Okay, so that's fine. So I choose one of this R1 or R2, one of this R1 or R2 for that. I have to choose it. I'm forced to choose it. Otherwise, there is no way I can satisfy this equation. Already for n equal to 0, I cannot satisfy this equation, right? But once suppose I have chosen one of them, R1 or R2, then I go ahead. So the n equal to 0 part of the equation is satisfied. Now you go to n equal to 1, n equal to 2, and so on and so forth. Okay, and start determining from this equation, right? This you can keep doing unless for some value of n, this becomes 0. You see, suppose for some value of n, this combination becomes 0, right? Then you cannot determine Cn from this equation, right? So that's the thing. So we will, I think, yeah. So let me do the following. Let's say, no, I erase this. No, it's okay. It's okay. This was just to tell you what is the meaning of A naught and B naught. Okay. So, I mean, now there are various possibilities, right? So, I mean, there are possibility, of course, R1 may be equal to R2, right? That could happen for some special values of A naught and B naught, right? But what we'll do is that we will consider the situation where okay, there are two possibilities. So we'll classify in the two cases. One, real R1 okay, I will call. I mean, I have to give a name to R1 and R2. Okay, so real part I will call R1. So this is a definition. I give a name. I mean a notation. R1 is the root whose real part is larger between the two. Whose real part is larger. I mean, so there is a real part of there are R1 and real part of R2, right? If the one whose real part is greater than the other, greater than or equal to other, okay. When it's equal, of course, you cannot distinguish. But when it is greater, I will call that as R1. I will call that as R1, not R2. I mean, this is giving a name to it, no? So is a root whose real part is larger than the other, than the other root, than that of the other root. Then R2 is other root. So the real part of R1 is greater than, so what we are saying is the real part of R1 is greater than real part of R2 or equal to, greater than or equal to real part of R2. This I can always do, right? I mean, the two possibilities, either two real parts are equal or two real parts are different, right? In the case when they are different, I call R1 the one whose real part is greater, right? That's giving a name to it. So it turns out that this coefficient for any n will not be 0 if you started with R1. Here, if you started with R1. Okay? I mean, it's not difficult to see. I will come to that point. So that is one thing. Because okay, let's see when this can be 0. You see, I mean, is it possible that this can be 0? After all, look, this is the quadratic equation for R. R is unknown. I mean, look at this equation here. So, question is, let's see when this can be 0. This can be 0 if n plus r is also a solution of this equation, because this is nothing else but replacing r by n plus r, right? So, so what we are saying is that r is a root of this equation, and also n plus r is a root of this equation, right? If that happens for some n, then this can vanish, and then we will not be able to determine the solution, because this equation becomes undeterminable somehow, right? So, but I mean, if I choose R1 as R1 where R1 is defined in this way, right? I mean, this will become R1 plus n. So the real part of this guy is even greater than real part of R1, because n is positive, right? But we know there are only two roots of this solution, R1 and R2, right? So the only other possible root could have been R2, but real part of R2 is less than real part of R1, less than or equal to, right? So there is no way this will vanish for any positive n, if I choose this value to be R1. Okay. Second, actually, even if I had chosen R2, if I had chosen R2 here, then it is possible n plus R2 for some particular value of n, it might vanish. When? Only if that n plus R2 is equal to R1, right? Because the only two roots are R2 and R1, right? So if n plus R2 is equal to R1 for some n, then you cannot determine for the solution starting from R2, right? But that means that can happen only if the real part of the difference between real part of R1 and R2 is an integer. Okay? If it is not an integer, there is no problem. You can just start from either R1 or R2 and keep going through these recursion relations, and you will obtain the series solutions. For both linearly independent. I mean, we know there should be two solutions, right? The second order equation. So that both the solutions you can obtain by choosing one you choosing R1 and other choosing R2. There is subtlety appears when the real part of R1 minus real part of R2 is an integer. Okay, and so that we will see. We will discuss that next time. But so the main thing is this. So that there are two cases. One case when real part of R1 minus real part of R2 is not an integer. Okay, and the second case is when real part of R1 minus real part of R2 is an integer. So this case will be more subtle. We will discuss that. So in fact, what we will do is that in this case, as we said, for choosing R1, you can determine the solution anyway, right? So one solution you already know, one fundamental solution. Then we'll go back. Remember, in the very beginning, we said that if you know one fundamental solution, you can obtain the second fundamental solution by the method of Wronskian and all that. I don't know, using Wronskian, etc. You can obtain. So in this case, we'll determine the second solution by using the Wronskian rather than using the series solution. Of course, also for this case, you can use a Wronskian. There's no problem because that is a completely general method. If you know one fundamental solution, you can determine the second one. That you can always do. But in this particular case, already we have worked out. All you need to do is replace R by R2, and that will give you again the solution, right? So, okay, now I think maybe I should stop because basically now what I need to do for this is the issue of convergence again, right? I mean, so we have this recursion relations with the Cn, right? So since when I choose R1, this never vanishes, right? So I can determine all the Cn's, right, in terms of C0. Okay, and then the issue, of course, arises whether this power series is convergent or not, right? So we need to worry about that. So next time I'll discuss the convergence of the series.